Hello viewers, welcome to this series of video lectures on the course Electrostatics, Magnetostatics and Electrodynamics. I am Dr. Rajesh Thakur, Department of Science, Bhopal School of Social Sciences, Bhopal. In this lecture, we have taken the topic electric field and electric field lines. The various topic we shall be covering here is electric field and electric field intensity, electric field lines and the various properties of electric field lines, then expression for the electric field intensities which are generated by a point charge and a electric dipole. In case of electric dipole, we will find out the expression for the electric field both at axial and equatorial position. This will be followed by certain exercises at the end. So we are starting with the electric field. Electric field is a property of any electric charge or any charge distribution. Within the electric field, any charge or charge distribution that exerts force on another charged particles. Whenever any charged particle that is being taken in within the electric field, it will definitely experiences a force. Electric field is produced by different types of electric charged bodies like point charge, charged plates, charged spheres and combination of two or more charges, etc. See, electric field only defines the area within which a charge can exert force on another charge. But this force, that is what Coulomb force, that varies from one point to another, even within the electric field of any charge or charge distribution, that is defined by electric field intensity. Electric field intensity at a point within the electric field is defined as the Coulomb force experienced by a unit positive charge placed at that point. This unit positive charge is also known as a test charge, which is used to test the electric field intensity produced by any source charge. See, electric field intensity, it is a vector quantity. It is a vector quantity, and whenever we are having a source charge, suppose Q, we are having a source charge Q here, and this is what representing the electric field of that charge. And within the electric field, we are having a point P where we wish to find out the electric field intensity. Then we will place a test charge over here. Then, under the influence of this source charge, that is what capital Q, definitely this test charge will move outward. Since I have told you that electric field intensity is a vector quantity, then what about the direction of the electric field intensity? The direction of electric field intensity is always along the direction of the movement of the test charge, along the direction in which the test charge moves under the influence of given source charge. In another way, we can say the electric field due to a positive charge is always outward or away from it, and electric field due to a negative charge is towards it or inward, we can say. The mathematical expression for the electric field can be written as electric field E vector, that is equal to K, which is equal to 1 upon 4 pi epsilon naught, where epsilon naught is the permittivity of air or vacuum, into Q upon R square. Here R naught vector, that is what representing the direction of the electric field. I have told to you, I am repeating this, that electric field is always directed along the direction of the movement of the test charge when it is placed in the influence of any source charge. Next is electric field lines. See, what causes the force on the another charge when it is placed in the electric field of any given charge? This can be explained with the help of electric field lines. Electric field lines are the imaginary lines. They might be straight or curved, which comes out from a positive charge and they enters into a negative charge. In case we are having an isolated charged particle, if it is positively charged, then it will emit electric field lines and they will end definitely at infinity. But if another opposite charge, that negative charge, is placed in the vicinity of this charge, then the electric field lines which comes out from the positive charge, they will enter into the negative charge. There are certain properties of electric field lines. They always comes out from positive, they enters into the negative. The density of the electric field lines that suggest the magnitude of the electric field in a particular region. If they are more dense, they are very close to each other, that zone is a zone of higher magnetic field. And in case they are comparatively away from each other, that is a zone of comparatively weaker electric field. See, two electric field lines, they can never cross each other because At any point over the electric field lines, any tangent drawn that gives the direction of the electric field. But in case two lines of forces, two electric field lines, they crosses each other, then at the point of intersection, there will be a possibility of two tangents. And at a point, we cannot have two directions of electric field. That is the reason electric field lines can never intersect each other. Now here, in this slide, we have taken a charge Q and its electric field is calculated at a distance r from it. For that, we have kept a charge Q naught, which is also known as a test charge, at the point where we wish to find out the electric field. And initially, this Coulomb force is calculated, which is equal to K Q naught upon R square. Then it is divided by Q naught as here written in the formula. Then finally, we have the expression for the electric field E, that equals to KQ upon R square. Also, we can add here one thing, that at this point, since this Q naught moves away from this charge Q, then the direction of the movement of Q naught will be the direction of the electric field produced by charge Q at this point. Now next, in this slide, we have taken two equal and opposite charges. And whenever we have to calculate the magnitude of electric field produced by any charge, then in the formula, we have to take only the magnitude of charge. Since we have two charges here, one is plus Q, another is minus Q charge, and we have calculated the expression for the electric field at equal distances, that is what R here and R here. In both cases, the expression for the electric field magnitude will be KQ upon R square. So we can conclude that the magnitude of the electric field at a certain distance from a given charge is independent of the nature of the charge. The nature of the charge matters only when we have to find out the direction of the electric field. As we can see here, the electric field which is produced by this negative charge at this point will be towards it, and the electric field produced by this positive charge over here is away from it. And in both cases, the direction of the electric field is along the direction of the movement of the test charge. Now, here onward, we will be talking about the strength of the electric field which is produced by electric dipole at axial and at equatorial positions. So let us understand first what an electric dipole is. Electric dipole is a combination of two equal and opposite charges separated by a certain distance. That is known as what electric dipole. Electric dipole moment is one more important parameter related to the electric dipole, which is defined as a product of either charge. Out of these two, we can take the magnitude of any charge, either charge, and distance of separation in between the two charges. That is known as what electric dipole moment. It is to be noted that this electric dipole moment is a vector quantity, and it is having direction from negative to positive charge, or we can say it is having direction just opposite to the direction of the electric field. See, in case of these two charges, if we talk about the direction of electric field, the electric field in between these two charges will always have direction from positive to negative. However, the electric dipole moment will have the directions from negative to positive charge. Here we have written the units of electric dipole moment, that is what Coulomb meter. Now in this slide, we have calculated the expression for the electric field which is produced by an electric dipole at its axial positions or along the same axis in which the dipole is placed. Here we have taken a point P at a certain distance x from the center of the dipole. Again, the dipole length is 2L. Each charge is situated from the center of the dipole at a length of L, and expression for the electric field is calculated at point P. Here, this total electric field at point P is calculated as a vector sum of the electric field which are produced by the charge which lies at point A and the charge which lies at point B. See how the electric field is calculated. The expression for the electric field due to the charge at point A can be written by using the expression we have done earlier in the earlier PPTs. That is, this term is what K, then Q, and here we have a square of distance. If we are calculating the expression for the electric field due to this charge at here, then the distance will be equal to x plus this distance, that is what x plus L whole square. Similarly, the expression for the electric field due to a charge at point B is calculated at point P. it is clear from the figure that the electric field which is produced by charge plus Q at point P will be larger in magnitude than the electric field produced by a charge minus Q which lies at a comparatively larger distance. As we have discussed, the net electric field can be calculated by a vector sum of the two electric fields which are produced by minus Q and plus Q charge at point P, and the electric field at point P due to charge plus Q is greater than the electric field which is produced by charge minus Q at point P. Therefore, the net electric field can be calculated like this, that is 1 upon 4 pi epsilon naught, then Q upon x minus L whole square minus Q upon x plus L whole square. On calculating this, finally we have the expression for the electric field, that is 2p upon 4 pi epsilon naught x cube. Clearly, at point P, the direction of electric field will be along the direction of the electric field which is produced by charge B, as the electric field produced by charge B is greater than the electric field produced by charge A. Now, in the next PPT, we are having an electric dipole and we have to calculate the expression for the electric field at a equatorial position, that is a point which lies on a perpendicular bisector of the dipole. Let the point of observation lies at a perpendicular distance of y from the center of the dipole. Then the resultant electric field at this point Q, that is what EQ, can be written as electric field which is produced by charge which lies at a point A, and plus the electric field which is produced by a charge which lies at point B. Now clearly, the direction of the electric field at point Q, which are produced by two charges plus Q and minus Q, can be concluded by placing a charge Q naught at this point, at point Q, at point capital Q. See, due to the electric field strength of charge plus Q, a charge Q naught placed here that will move outward along this direction. See, therefore, the direction of the electric field due to plus Q charge will be along the direction EB, and the electric field which is produced due to minus Q charge will be along this direction. That is because a test charge placed over here will be attracted by minus Q charge towards itself. Here we have written the separate expressions for the electric field which are produced by the two charges at this point, and on calculating, clearly you can see here the electric field EB and electric field EA. These two electric field vectors can be resolved into two perpendicular components, and here we found that the vertical components or the sign components of these two electric fields, they are cancelling each other, and the net electric field only exists due to the horizontal component, that is what the cosine components, and we can calculate this by using this expression. And finally, we will have the expression for the electric field, that is this term represents K, 1 upon 4 pi epsilon naught, P, that is what dipole moment of this dipole, divided by y square plus L square raised to power 3 by 2. Now, we will solve certain exercises. The very first exercise is about, see, find the electric field at a point P located midway between the charges when both charges are positive. We are given with a condition in which we have to find out the expression for the electric field or total electric field due to these two equal charges, which is having magnitude 2.5 microcoulomb, and we have to find out the expression for the electric field exactly at its center. See, we know from the expression for the electric field, that is electric field equal to KQ upon R square. Since this point lies at equal distance from both the charges, they will produce equal electric field at this point. This charge as well as this charge both will produce equal electric field at this point, at the midpoint, and the direction of these electric field, the direction of the electric field which is produced by Q1 over here, that will be along this direction, that we can come to know again by placing a test charge at this position. Of course, a test charge is known as for its unit magnitude and positive nature. Then under the influence of this positive charge Q1, which is positive here, that will move along this direction, and therefore E1 will be along this direction. Similarly, the electric field due to this, that will be along this direction. As we have discussed, they have equal magnitude, then they will cancel out the electric field of each other, and we will have a net electric field at the center equals to 0. In the next question, we have taken a problem. See, 3-point charges are located at the corners of an equilateral triangle as shown in the figure. Calculate the electric field at a point P located midway between the two charges on the x-axis. Again, in case we have to find out net electric field at here, what we need to do is we have to find out the expressions of the electric field which is produced by the individual charges. See, electric field which is produced by charge Q1, the electric field which is produced by charge Q2, and the electric field which is produced by charge Q3. After calculating the individual electric fields, we can find out the net electric field by adding these 3 vectors by using basic laws of vector additions that we can use here, triangle or parallelogram laws of vector additions. And that part of this question I'm leaving as an exercise for you peoples. You can solve it. Thank you very much for watching. We'll see you in the next module. Thank you so much.